No. Vediamo. This is weird. Okay. So I think I can just, if I can close that, I don't need to see that. Okay. Right. So I'm not sure how many people we're going to have today, Rosella.
Yes, I imagine.
It's I think it's part of the season. I think everyone seems to be sort of running around doing stuff. Okay, I'll tell you what. We'll just wait a few minutes and see what happens. If it's only us, then it's fine. We can just go ahead and do what we want and tell everybody else that they missed something fantastic. Maybe. Okay, so how are you, Rosella?
Nice.
Fine.
Fine, yes.
Everything okay?
Yes.
What's the weather like?
Well,
in Malta.
Oh, it's nice. The weather is nice. Just a bit cold, but not like Sicily probably.
Ah, okay.
Because
so it's sort of
so
it's because here it's just gone a little bit cold over the last few days. It's I think it's Anna. Ciao, Anna. Yeah, it's going to go down to about 1 or 2 degrees this evening.
Hi, Gordon.
Hi, Anna. How are you doing? Are you okay? Tutto bene?
Yes, thanks.
Okay.
Tutto bene.
Okay. I was just saying.
Gordon,
tell me.
Non so se mi devo staccare un po' prima per la gestione figli.
Ah, if you have to, you have to.
Okay.
It's okay. Yeah, I was just saying, I don't know how many people are coming this evening or this afternoon, because a couple of people sent messages on the chat saying that they have meetings, school meetings. So maybe some people will be joining us a little bit later, I think, maybe. So anyway, just wait a couple of more minutes and then we'll start, just to make sure that give people a chance, if you don't mind. So maybe what I need to do. Okay, vabbè. There's no Stefano either. Okay. Ok, allora Antonio, scusatemi, non riesco a collegarmi, provo a raggiungervi durante il corso. Dove mi trovo? Oggi non riesco a collegarmi. Questo è Salvatore. Ok. Allora, okay, I'd say that we should make a start. That way we can sort of move on. So So last time we were talking about, I think we were talking about density.
Sì, materials.
And materials. And we will exactly. And so we were looking at sort of different ways of describing different properties of materials. So what I wanted to talk about a little bit today was I wanted to start with something about density, just to finish that chapter, and then I wanted to move on to something which is more, which is also, let's say, part of classical physics, which is optics, but just a few, let's say, a very basic introduction, a very basic demonstration of a couple of things that you can actually sort of try. You can try at home if you like, or you can try with your classes, because it's an area which is obviously widely used in everyday life, but perhaps we take a lot of it for granted. Okay, so just sort of coming back to density. What we've got is this idea of how much matter, how much material we have in a particular volume. So we've got this. Get rid of the mouse. So we've got this idea of a density as being some sort of measure of mass over volume. So I'm just keeping this open so I can see if someone else is trying to get in. Okay, so we've all heard of the Dead Sea. Has anyone been there? Rosella, have you ever been to the Dead Sea? Oh, you've got Ivo.
Oh yes, I know.
Have you been there?
No. Just okay. I know, but I haven't been there.
You haven't been there. Okay, Livio, have you ever been to the Dead Sea?
No.
No. Anna?
I'm sorry.
No. You don't have to apologize.
Maybe in the future.
Well, yeah. Maybe. Anna, have you been there? No. Yes. Hello. No, you've never been to the Dead Sea. Ivo, you look like a man who has traveled.
No. No. I never been there.
You've never been there. Okay. So what can you tell me about it? Do you know anything? What do we know about the Dead Sea?
That there is to Ivo. Okay. Sorry.
No, anybody who wants to. So it's just una alla volta. Come diceva
Figaro. A very high concentration of salt.
Yeah, it's a very high concentration of salt.
Its water has a very high density, and swimming is difficult.
Yeah, so it's a very high salt concentration. I think Ivo is.
Sorry. Okay.
No, it's okay, because you were going to say something, Ivo. Stavi per dire qualcosa. You were going to say something.
No problem. But about the salt, okay, I agree.
Okay. So why do we call it the Dead Sea?
Because the life, probably microbes, some microbes.
Yeah. Okay. So yeah, probably. Well, normal animals, fish and stuff.
But some
won't leave there.
Chemistry said about the salt of the Dead Sea are very useful for some disease.
Okay, yeah. So this is where you get into the idea of like the thermal waters or the the muds, you know, the what's that called? Oh, there's a Greek word which I can never remember. It's a type of therapy which is using hot mud, for example. Something like thalassotherapy or something like that, but it's not that. Yeah, so yeah, people there are many mineral springs around Europe, and maybe the Dead Sea is obviously not in Europe, but it's an extreme example of a solution which can be used, or which has been used for medicinal purposes. I think people sort of tend to be drawn to these things. Yeah. So yeah, it's a potentially interesting thing. But I just want to come back to something that Rossella was saying, which is maybe some microbes. And
can live inside.
Yeah. Well. Do you know what these things would be called? Because
I don't remember. I studied them many years ago, but in Italian.
Okay. Wow. Okay. Well.
Yeah.
Good. Yeah. Halophiles.
Okay.
Yeah, they're the halophiles. Okay. It's a fascinating, absolutely fascinating area of biology, which, well, I sometimes say if I was going to do all of this again, I would maybe actually become an engineer, but I'm not sure, because extremophiles are extremely interesting. So halophiles, halo from the Greek meaning salt, okay, as in we get from which chemistry we get the halides and the halogens, okay. I'm sure there is a book in this somewhere. Rossella?
I can see your what you
can't see it.
You are writing.
You can't see it. Am I not sharing?
No. Okay. Now. Okay. My problem. Sorry.
Okay. No. Okay. Okay. Because it says that I'm sharing here. So okay. So yeah, and it's interesting because these guys, it's only sort of relatively recently that people really started to appreciate that life could live in such extreme conditions. And of course, here the extreme conditions are it's osmotic. It's the concentration of the salt which causes problems for living organisms. Okay. Yeah. Do you know of any other? Just while we're on the subject, do you know of any other extremophiles, or have you heard of any other places where people find them?
Yes.
Got any ideas,
Rossella? For instance, in the near, I don't know, in a volcano or near the Thermophiles.
Yeah. Okay. So we've got volcanoes. So we've got the. I'll tell you what. I'll write this up here. So we've got the Thermophiles. Yeah, I once had a fascinating conversation on a plane with I was going to the States for work, and I was sitting next to this guy who was reading what looked like really hardcore academic stuff, and it looks a bit like biochemistry or biology, something like that. And we got talking, and it turned out that this guy, I found out later, this guy is actually a world expert on thermophiles. Hi, Marina.
Oh, hey.
Are you on a plane, a train, a boat?
No, I'm in the street.
You're in the street. Okay.
Now I take underground.
Right. Okay. Yeah. So this guy, he was I found out later he was a world expert on thermophiles, and he told me about how he went to he went collecting these things in Antarctica, in the volcanoes in Antarctica. It's just unbelievable. It was like boys' own science stuff. It was fantastic. Anyway, so yeah, so you got thermophiles. And of course, they find secrophiles. These are the cold ones. Mm-hmm. These are the ones that they're finding in the ice cores in Antarctica and so yeah, these are, it's fascinating set of organisms. And of course, one of the key, do you know the PCR, polymerase chain reaction? Okay, so this is the DNA amplification method. Yeah, this uses an enzyme which comes from a thermophile, which the original one was actually isolated off. It was either Stromboli or Vulcano. It was isolated in that area because under the sea there are thermal vents, thermal plumes, they're called, volcanic plumes, and they found these bacteria living in these conditions. And the reason is the enzyme is used here because they have enzymes which work at 60 or 70 degrees centigrade. Okay, so you can do they're very, 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 very efficient at working at 60, 70 degrees centigrade. So you can do high temperature reactions. So that's the thermophiles. Okay, but we weren't talking about thermophiles. We were talking about the Dead Sea, which might not be quite so exciting. Okay, but what I've got here is I've just got a little exercise. This is a sort of more like a languagey sort of exercise here. I'm just going to ask a couple of questions though, because if we think about salt water in general, a first question would be, why can't you drink seawater? Why can't we?
Because of osmosis.
Mm-hmm.
Because in seawater there is a higher concentration of salts than in our cells.
Mm-hmm.
So our cells would lose water outside through the membrane.
Yeah, so I mean, basically, it will. It's not very good for your kidneys. Basically, yeah, you have this serious. Osmotic balance problem. Now, Ivo has just disappeared. Now, I don't know whether that's because he's having trouble or because he's non riesco a collegarmi, Anna. Yeah. I don't know what to say. I don't know what to do. Because the message from Stefano was very confusing. There was all sorts of numbers and stuff in there. But if you guys connected, these guys should be able to connect too. So maybe Anna can try again. Okay. So as maybe a sort of an obvious question, the difference between seawater and fresh water.
Mm-hmm. Fresh water is from in the lake, in the river.
Yes. Okay. Yeah. So what's the big difference?
The concentration of salts.
Mm-hmm. Yeah, it's the concentration of the stuff that's dissolved in it. So it's typically a lot less salty than seawater. Now, this is something which you might not necessarily relate to density, but what happens to a ship when you load it with cargo? So you have a ship in the sea. This is the Red Sea, by the way. Sorry. It's a really bad joke. Okay. What happens when we load it with cargo? So we start putting lots of stuff in it.
The stuff, yes.
So what happens to the ship?
The level go down a little, not so. Depend of the cargo.
Well, let's say that this is a lot of lead. Okay, so for some reason this is a ship that's carrying a lot of lead. So yeah, so you would expect it to go down in the water, wouldn't you? Okay, so the level is, so the ship is full of this stuff. Okay, and so it's going to float lower in the water. Okay, right. So another question is the temperature of the sea the same in all parts of the world?
No.
No. Okay, so what sort of differences do we have?
Because there are the streams, the correnti.
Okay, so we've got currents.
Currents.
Okay, these are the ocean currents. Okay, ocean currents. Okay. Can you tell me something about those?
I think I'm not an expert, but I think about the different of the temperature and the difference of the density.
Okay, so yeah, so we've got temperature differences and we've got density differences. Yeah. Where is so if we think about temperature, where is the sea? Where is the oceans warmest?
The equator.
Okay, so around the equator.
Around the equator.
Yeah. Okay.
And
what about the? So this is, let's say this is hot. What about the cold?
And the pole. On the poles.
At the poles. That's got nothing to do with Poland. Okay. It's to do with the extremes of the Earth. Okay, so okay, what about the density though? What about the density?
Where the water is colder, the density is higher.
Okay.
For thermal dilatation.
Okay. So this and so the equator, at the equator you have low density, yeah? Yes? Correct? Livio?
Yes.
Yeah, okay. So what do you think, what influence do you think that has on the ship?
That the same ship with the same weight stays a little higher in cold water and lower in warmer water.
Yeah. Okay. So that means, that does mean that I mean, considering, okay, we think, okay, well, this must be a relatively small effect, but you have to remember that these ships are very big and they're carrying a lot of stuff. And even in the 1800s, when ships were not quite so big, they still carried a lot of stuff. And this was definitely, let's say, a practical problem which people had to deal with. You may or may not have heard of this Plimsoll. You may have heard of this, called a Plimsoll line.
No.
No?
No.
Okay. Well,
maybe we can understand now after your explanation.
Let me just. I'm going to draw something here. Now, this is not accurate because it's. I'm drawing this from memory. Have you ever seen something like that on the side of a ship, or a set of lines? They're typically in this part of the ship. Okay. These are Plimsoll lines. And you will notice that there are some letters by the side of the ship, by the side of each line. And what this refers to is how high or low the ship stays in the water according to where it is in the world.
It is in Italian linea di galleggiamento.
Sì, linea di galleggiamento. In English, it's called the Plimsoll line because of the guy who invented it. It was 1850 or something like that. And this is another one of those curious pieces of history where obviously the problem in the 1800s was there were many problems with traveling around and moving stuff, but for the British Empire in particular, the problem was to make sure that ships got safely to where they were supposed to go. And Plimsoll petitioned Parliament to legislate that all ships that came to Great Britain had to have this, let's say, this measurement on it, which was to stop them from being overloaded. Because without an idea of how high the ship is floating, it was very, very easy to overload ships, and many ships were lost because of that. Okay, so in a way, it was an economic imperative. Okay, but there's a very practical, let's say, a very practical reasoning behind it, because Britain is in the North Atlantic, and so the water is cold and it's pretty dense. Okay, so if you're going from Britain to America, it's one thing, but if you're going from Britain to Buenos Aires, that's something else, because you have to go past the equator, which means that you're going to potentially be traveling lower in the water, which means that you may not have enough draft to overcome storms and what have you. Okay, so that was what this was. This Plimsoll thing was about. So,
but, do you know how much could be the difference of level?
Oh, well, it will depend. It will depend on the ship. It depends on the type of ship. But if you go to, well, let me just see if I can find something on the web, because if you go to a port, you know, go to Geneva or somewhere like that, or Venice, Mestre. I think my video is probably blocking up because I'm overloading my computer a little bit. But anyway, let me just see if I can find a picture. Plimsoll line. Okay, just 2 seconds. You can find. Okay, so I'm just going to put this on here for a minute. Okay, so you know, these can be quite big actually. So the difference can be the difference. If you look at this one, for example, the difference can be quite sort of quite a big difference. The thing here is that you also have to remember that the sea is not always calm. So even though it might not look, it might be 1 meter or 2 meters, but that 2 meters could make the difference between the ship being stable in a storm or not. Okay, so this one I think actually tells us the names of these. So you have these different letters, and so what you have is tropical fresh water. If you think about it, it's a density scale basically. Tropical fresh water is the least dense of the water that you can find on the planet. It's warm and it's got no salt in it, or it's got very little salt in it. Okay, so this means that your ship is going to be really sort of low. Okay, fresh water. Then you have tropical seawater, so that's the equator, in the summer and in the winter, because you also have that problem as well. And then we have the winter in the North Atlantic. So if you want to carry lots of stuff, that's probably the best time to do it, but it's probably not a great place to be because the winter in the North Atlantic is not exactly a calm place to be. Okay, so this is the Plimsoll line, and you see it drawn or painted on all ships. Yeah. So, Rosella, you live in Malta. Do you live near the port or?
No.
Okay.
Malta is very small, but I haven't never been in the commercial port of Malta.
Okay, yeah. Well, it's a typical thing. I mean, I think you'll find them on cruise ships as well. So.
Oh, okay.
Or any ship that is floating, anything that's floating, you'll find them. Okay. Because of course here the problem here is that these tend to be quite tall, so it's the stability is the problem.
Okay. Then in Valletta there are many.
Yeah.
Now I don't think, but usually yes.
Yeah. Okay. Yeah. This is a quite extreme example here. Okay. But okay. No, I just thought I'd show that because we were talking about density and stuff. Now I think this next part is sort of like an exercise. It's like a closed type of exercise. Yeah. So what I'm going to do is I'm just going to increase that to the size. So someone is on the chat. Someone's on the chat. Can I just open that and see where's someone is on the chat. Who is it? Sorry, I had problems with connection. That's okay, Anna. It's happening. Okay, so I don't know how you feel about sort of maybe reading out stuff online. Okay, so what if you want to, you can. If you don't want to, it's not a problem. So Rosella, do you want to read this?
Of course.
Why not? We're only young once. We're immortal on the web. So
the first part.
Just go with the first part.
Sorry for my pronunciation. Okay.
No, it's okay.
Okay, it's okay. Mark Twain described a swim in the depth sea as a funny bath, which left him shining like an icicle, with white salt crystals on his skin and smelling a little bit odd. It's a major tourist attraction, and swimming in it is a strange experience because you can't really swim properly as your body remains too high in the water.
Yeah. Okay. Icicle.
The ice, the big ice.
Icicle. Ghiacciolo. Yeah.
Okay.
It's the
big ice in water.
Yeah. Okay. Right. Okay. So this is where we need to find some words now. So, Ivo, do you fancy trying?
The second line. Block.
Can you do this one?
This C, which is I think Dead Sea.
Okay, so this C, which is now, it's one of these words down here.
First, this is located.
Yeah. Okay. Good.
Between Jordan, Palestine, and Israel is really a lake fed only by the river Jordan, and is one of the saltiest bodies of water on earth.
Okay. I was just thinking, can you think of another famous salty body of water in the United States?
Yes.
Yes.
Salt Lake City.
Yeah, Salt Lake City. Yeah.
Okay. Famous by the skiing.
Yes, absolutely. Okay, right. I don't know, Livio, do you feel like you want to try, or?
Yes.
It's okay. It's okay if you don't want to. It's not a problem.
It is called the Dead Sea because no life can tolerate the harsh conditions of the highly saline environment. The water here is a lot saltier than the open ocean because the river and the rain water wash.
Yeah.
Wash should be washes.
No, because it's the river
and
the
river
rain.
The
rainwater.
And the rainwater wash salt out of the rocks of the surrounding hills, bringing them to the lake where they concentrate as the water evaporates rapidly under the arid conditions of the climate.
Okay, so what we've got is we've got this sort of physical process of, let's say, extraction of the soluble stuff, and then you've got the evaporation, which is just basically concentrating the salt in the water. Okay, so let's see if we can. Okay, so I don't know, Adna, is your connection good enough?
Yes, it's okay now.
You want to try?
Yes, I would like to try.
Okay, bye.
Common salt is made up of sodium chloride, which is very soluble in water. The water in the Dead Sea contains a lot of salt, and more it contains, the denser the water is. This means that the saltiest water is at the bottom of the sea, where it cannot contain and more sodium chloride, which crystallizes out, forming a layer on the seabed.
Okay, so do you understand what's happening here? You got a picture? Okay, so basically, if we think about it, what we've got is we've got the basin of the Dead Sea is like this. Okay, and the concentration of the salt is getting more and more dense. Okay, so there's more salt at the bottom, and it's so salty that you actually have salt crystals. The floor of the sea is covered in salt crystals. Okay, so it's crystallizing out. You can't get any more salt in there. Okay. And if I remember, near Salt Lake City, there are the flats, the salt flats. And what happens is when all of this evaporates, you're just left with a layer of salt, basically. Yeah. So this is if there is no more water gets into the Dead Sea, and apparently they have problems with irrigation because they take too much water out of the Jordan. Okay, sooner or later the Dead Sea will just be a salt flat. Okay. Okay, so Marina's she's on a metro now because I can see the luggage rack above her head. So I won't ask her to participate in this bit because she'll be too embarrassed. So Rosella, could you go sort of carry on a little bit, please?
Okay. Seawater contain about 3.5% sodium chloride.
Yes, chloride. Yeah,
chloride, along with smaller quantities of other salts. The Dead Sea.
Dead Sea.
Sorry.
Dead Sea. Dead.
Sorry,
That's it. Dead. Okay.
The Dead Sea is getting saltier because a lot of water is from the river removed from the River Jordan for agriculture in the surrounding countries. These affects the amount. Reduces the amount of water and increases the concentration of the salt in the sea. And because of this, the sea is receding at the removed. No, please. Rate.
Okay.
At the rate, of 1 meter.
If you like, the velocity.
1 meter per year, which is a cause for alarm. However, scientists have found that in the past there were periods when the sea contained no water, and the area was covered with salt deposits.
Okay, so these things are cyclical. So in the past, the Dead Sea sometimes has been a salt flat. Yeah, this is it's quite curious. Okay, and I think this might be the last. No, it's not the last one. Okay, Ivo, would you like to take this one?
Okay, the salinity of seawater is important for ships traveling on the ocean because it affects how much cargo a ship can carry. When a ship is loaded with goods and materials, it sinks lower in the water. If it carries too much cargo, it will be too low in the water, and there may be a risk of sinking during a storm when the sea is agitated.
Okay, yeah, when the sea is rough. Okay. Okay, Livio, do you want to carry on here?
This was recognized as a problem for merchant ships.
Merchant ships.
Merchant ships in the 1800s.
1800s. Okay.
1800s, when ships started sailing around the world more as a global trade. Expanded between the colonies of different countries. Samuel Plimsoll, a member of the British Parliament, was concerned that many ships and sailors' lives were lost at sea because of this. So he invented an easy way of seeing whether a ship was overloaded or not. His invention was called the Plimsoll line, which all ships must now have painted on their sides. It gives a measure of how much cargo can be safely carried by the ship, and it shows how this can vary according to whether the ship is sailing in fresh water or seawater, and whether the water is warm or cold.
Yeah, okay, good, good. Let me just, I think this is the last one. So Anna, do you want to just try this last one?
Yes. The varying density of seawater in different parts of the world is also very important in creating and maintaining ocean currents, as bodies of water of different densities move around the oceans. An important example is the Gulf Stream, which brings warm salty water towards Europe from Gulf of Mexico and influences the climate, giving the continent a milder climate than would be expected for its latitude.
Okay, so just a small note here: climate.
Climate. Okay,
okay. But that's fine. Okay, and that's a diagram of the Plimsoll line, which we've sort of already discussed. Okay, so I'm not going to go any further with this particular set of slides, I think. So any questions or comments about this? No? Okay. Rosella?
No.
No? Okay, fine. Okay, so what I thought I'd do today, as well as just finishing that stuff about density, I wanted to do this, which let's just see if this works, because okay, so now this was a reading, but I don't want to do it quite like that. Okay, so if I asked you about lenses, what can you tell me about lenses?
There are here lenses.
Okay, so we got spectacles. Okay, so this is eyesight. This is correcting eyesight, isn't it? Okay. What else? Anything else about lenses?
Where we use lenses, or also what are lenses?
Okay, so you can tell me anything.
Well, so where we can find lenses could be in our eyes.
Okay, yeah. So we've got eyes.
Natural lens.
Okay, so this is natural. Okay.
I don't know the pronunciation of cristallino in English.
Okay, crystalline.
Crystalline.
Are you talking about the protein in the eye lens? Yeah, it's a crystalline protein. Yeah. Okay.
And in telescopes, microscopes.
Okay, so we've got telescopes, microscopes. Okay, so we've got
microscopes, magnifying lenses.
So we've got instruments, okay. And yes, so we've got magnifying. And of course, we also have the magnifying glass, of course, which is a type of lens. Okay.
Yeah.
Any?
They are made by glass or plastic.
Okay, so we've got materials. Glass, typically, or plastic. Now that suitable plastics have become available, a lot are made of plastic, and they can be pretty good actually, considering. Okay. Any other things that you'd want to say about lenses?
Would be convex.
Okay. Now this is getting a bit more. Getting a little bit more technical. Convex.
Or concave.
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 Okay. Okay, so this is optics now, isn't it? What's the difference?
Of course, the shape and convex lenses tends to concentrate light.
Okay.
So if they receive parallel beams, they concentrate them in one point.
Okay.
At a specific distance.
Okay.
From
do you remember
lens.
what that point is called?
Focal point.
Yeah. Okay.
So or focus. Focal or focus.
Focus point or focal point. Okay. Either will do. Okay.
While concave lenses make parallel beams to diverge.
Okay, so these are divergent. And these are convergent. Convergent. Okay, yeah. Okay, it's a little bit messy, but this is okay. It's just a mind map in a way. Okay, things like sort of different points. Okay.
Maybe colored lenses and the transparent.
Okay. Yes, we can think about different types of colors, transparency. Yeah. Polarizing, maybe. No, polarizing is more filters, I think. So I'll leave that one out. Okay. But yes. Okay. But maybe yes. I mean, if you're thinking about spectacles, you might have a pair of polarized eyesight spectacles, maybe. Okay. Right. So what I wanted to do today, as I say, I wanted to talk about lenses, but I've got something to show you. So I'm going to switch some lights off here because I need this to be a little bit dark. So if you just bear with me for 2 seconds. Right, okay, now let's see here. This will work. Okay, yes, you can see these things. So just okay, so what I've got here is I've got a, it's a piece of gelatin. Okay, if you want to see it, sort of like a wobbly piece of jelly. Okay, and what I'm going to do, I've got a laser, if this will actually work. And well, yes, there we go. Maybe we can see that. Sort of, it's a little bit maybe I'll tell you what, see if I can do it the other way, because it's to do with the overexposure on the webcam, which is, I'll see if I can take that down a little bit. Let me just bear with me 2 seconds, because device
excuse me,
properties.
Gordon.
Yes, tell me.
And now I have to leave the lesson.
You have to leave. Okay.
Leave the lesson.
No, it's okay.
Okay. See you another next week.
Next week is, I think it's number 7.
Okay.
Next week is number 7. Okay.
Right.
Right. So okay. Bye.
Bye.
Okay. Right. There we go. Now this is far too strong. So let me just see if I can use the red one, which might be a little bit easier to see. Okay, let's just have a look at this one. Now, I don't know whether you've ever done this. This is quite a, I thought this was quite a neat experiment when I first saw it. Is this switched on? Yes, it is. Okay. Ah, there it is. There it is. Okay, so what you can do is you can use gelatin to make lenses, and the cool thing is that you can actually see the beams through the lenses. So in this case, this is a spherical lens, okay, and this has spherical lenses, as Livio will tell us. What's the problem with spherical lenses, Livio?
The problem?
Yeah.
I don't know. Actually.
Okay. No. It's just I thought you sounded like you were sort of quite an optics guy. So I'm just going to put that on there so that I can actually write. Okay. Okay. So the thing is, okay. So if you look at this, the beam is sort of coming out like that, okay? And of course, if I move it and I get this just right, I need to get this just right, you can actually see the beam is coming across and it's sort of coming down like that, okay? And if I move it this way, you can see that. Now, I can tell you that it looks a lot better than it does on the screen, simply because there's the webcam is not as sensitive as it could be. But what you can see is it's sort of it's coming out like this way, and it's coming like that. Okay. The problem with spherical lenses is that they come to a focal point which is not very distinct. Okay, because the lens is basically the wrong shape. So what happens is you get a focus which goes from about here over to about here, okay, something like that. But this, let's say this setup actually allows you to see the rays. It's to actually see the ray of light as if it were in the book, just like in the textbooks. Yeah. And I think this is really cool, because you can see how as I move it, I'm just keeping this parallel. Okay, so I'm not moving I'm not sort of angling it. Okay, I'm just keeping this parallel, and I'm just moving this, and you can see how it moves, how the beam changes direction. Okay. Now, as I say, I think this is a pretty neat trick, because it allows you to look at the difference between the different types of lens. Now, this is a very badly very, very badly cut convex lens, okay, which is maybe, if I've done this right, it will be easier to see this. Okay, so there it is. It's sort of coming straight through.
Is it made by common animal gelatin?
Yeah. It's pane degli angeli.
Mm-hmm.
Okay.
It's very interesting. Very, very interesting. No, the fact that you can see the light inside the lens.
Yeah, that's
so
right.
The effect of refraction is very, very.
Yeah, and the
cool.
reason why you can see the beam of light is because gelatin is a colloid. Mm-hmm. So what's happening is as the light beam sort of passes through this shape, what actually happens is the beam is bouncing off the protein molecules in the colloid, and so it's so you get this is Tyndall scattering. Okay, and so this allows you to see it's exactly the same effect as when you shine a laser through smoke or through when you see sunlight through clouds. Okay, so, and again, what you can see here is that this, as I say, this is, I mean, I'm not going to be able to draw this very well, but this has quite a different, if you do it properly, this has quite a different sort of behavior with respect to the spherical lens. If you cut this well, you can, just one second. Yeah, if you cut this well, you can actually, you really can see it sort of come to a focus. Okay, so it can be really sort of quite impressive. But the one which I think is the best is this one. And let me just get rid of that. When I made the spherical lens, this doesn't look fantastic, but when I made the spherical lens, I basically had a square of gelatin, okay, and I used a glass to cut the spherical shape. Okay, so I had this sort of situation. Okay, now I thought, okay, well, you can take that away. This is something I can use. It's the spherical thing, but I will try not to break this because it is a little bit delicate. Okay, let me just put that up there. Okay, so what we've now got is a concave lens. Okay, and I think this is the one which I think is the most impressive, because you can see how the light goes through, but when you get up here, you can see how the beam, let's see if I can get this, you can see how the beam starts to come this way. So it's being so essentially you can see how, just as in the textbooks, the focus is in front of the lens. It's a virtual focus. Okay, so I think this is really quite a nice demonstration of lenses. Now I'll tell you what I'm going to do. I'm going to try the other laser again, because maybe for this one, if this one will work well. So this is an ultraviolet laser. It's more UV rather than visible. And okay, come on, there you go. Oh, come on, there we go. It has a bit of a dodgy switch, this one. Come on, there we go. Okay, so as I move it, it's maybe overexciting the thing. What I've done is I've put tonic water aquatonica in the gelatin, because the tonic water is excited by the ultraviolet. So you can see it's decided not to play today. It's the usual thing. Someone sent a message. No. Okay, that's there we go. So you can see how if I move this, okay, it's sort of it works like a concave lens. Okay, so it comes to a negative focus. Okay, so let me just pull this up again, and so the situation is this: if you do decide to do this, it's really quite easy to do. You just need to take a piece of gelatin, just cut the pieces into you need a circle. So you can use a glass as a cutter. You can keep the external parts and you put them together in the other way, and you get the concave lens. Okay. So as you move the laser, you can do this sort of properly, and you can set it out, and you can measure it, measure the movement of the laser. When you use the spherical gelatin lens, as I say, if you manage to get a good sphere, you can see that the beams don't actually converge very well. There's a sort of an area where they're sort of overlapping. And this is typical. This is typical of spherical lenses, which are it's so-called spherical aberration. Okay, so we have aberration. Okay, and what you have is you have this situation, and the ones in the middle are they're focusing sort of in a slightly different place. Okay, so the focus is indistinct. Okay. If you do manage to, this is not spherical, this is a mistake here. If you do actually manage to make a decent convex lens, this does come to a focus. This does converge. It can work quite well if you have a little bit of time, a little bit of patience to cut it properly. It can work quite well. But as I say, I think this is the best one, because this is the one which, because this type of lens, the idea of a virtual image, it's very, very strange. And so when you see these things in the books, you think, how can that work? How can that possibly work? But this actually shows you where the beams are going. And I think this is a very useful demonstration, an optical demonstration of this, of the difference between concave and convex. Okay, I'm not going to do that today because I haven't got the stuff set up. I'll do that next time maybe. So, got any questions about this? This is really easy to do. È molto facile.
Gordon, would you mind to repeat?
Mm-hmm.
They have a circle lens.
Okay.
The focus.
Okay. Yeah. Okay. So basically, what happens is.
Okay. This is a spherical.
It's okay. Now this is a cross section. Okay. So typically let's say the first types of lenses that were made, it's easy to make spheres. It's easy to make spheres, or easier to make spheres, and it's not so easy to make proper concave, because the proper concave convex lens has to have the right radius of curvature. Okay, so the way this is curved, this will be part of a circle, of course. Yeah, so this radius of curvature has to be the correct shape. It's easy to make spheres. Okay, but you can, let's say in this system, what we're doing is we are taking a cross section. So we don't have a true sphere, but we have a cross section of a sphere, which is a circle. So what happens is basically, because of the way the parallel rays hit the sphere, and because of the amount of glass which they're going through, they are refracted in different ways. Okay, so what happens is you get, I've exaggerated it here, okay, but you get a part coming to focus here and a part coming to focus here. So the image is indistinct. Okay, it's out of focus.
Okay.
Yeah. Okay.
Yeah.
So the image is out of focus. So how do you get around this? Well, or how do you get around this? You get around this by making a lens which has this shape, this convex shape.
Okay.
Okay. And so this has just enough space to cause the refraction like that. Exactly the same here. Okay. This is just the right amount to bring it to focus here. And of course, this is actually, it's it's easier to draw than it is to do.
Okay,
course,
I understood now.
Yeah. Okay.
Yeah.
Okay. Right. Okay. So what I thought we'd do is just thought I've got another little reading exercise, which is actually to do with the history of this stuff. Because so this is we have the microscope, the telescope, and this is the geloscope. Okay. Let me just go through here. So we've got this thing which you may or may not have ever noticed. If you put a drop of water on a tablecloth and you look closely at it, assuming that the drop is sitting, typically if it's on like a nylon tablecloth or a plastic tablecloth, the drop of water is sitting proud. It's almost spherical. So it's almost like a spherical lens. So what you might notice is that the fabric underneath is actually magnified. Okay, so this is a very simple, let's say a very simple magnifier, which is fairly easy to come across. Okay, now, as I say, this is another one of these closed type of exercises. I wasn't quite sure how long this was going to take me today. So I'd like to propose that we just go through this exercise, and this sort of talks about where some of these things come from, and maybe you'll recognize some parts of the some names and some parts of the history here. So, Ivo, would you like to start?
Okay. Can you hear me?
Yes, absolutely.
Okay. Have you ever looked through a drop of water on a piece of cloth? Did you see the fibers on the cloth more clearly? Did they appear to be bigger than normal? The drop of water is acting as a I don't know, as a spherical? No. As a lens. Okay, thank you.
Good.
As a lens, something which alters the way that light passes through it, giving rise to an effect of magnification.
Yeah, magnification. Okay. Right. Do you just want to read the rest of the page?
The Romans discovered how to make pieces of glass which were thin at the edges and thick in the middle to focus the sun's rays and concentrate heat on an object. The English word lens comes from the Latin word lentis, meaning lentil, because they looked like lentils.
Lenticchia.
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 It's similar.
It's the way all of this sort of stuff seems to come around. Okay. Yeah. Okay. So, Livio.
It's nice to see when water drops, small drops of water. When you look at your smartphones and it's raining, and small drops fall on the display, and you can see the pixel, the colored pixels in the white display.
Yes.
Very nice.
Yeah. No, and in fact, I mean, the magnification, it will be maybe 3 or 4 times. It's not a big amount, but it's enough. It's enough to just sort of take you into the world of the small things. Yeah.
Yes. So microscopes are instruments to study things which are too small to be seen with the eye alone. There are 2 types of optical microscope. Simple and compound microscope.
Yeah.
The first is made of a single lens, while the second is a combination of lenses. In both types, light passes through the sample and the image is magnified. The compound microscope, which uses 2 or more lenses, was invented in the 1500s by Dutch spectacle makers Hans and Zacharias Janssen,
I would imagine.
Although the best magnification they achieved was only about 9
times. Yeah, the X. Yeah, good point. The X is we read it as times. Okay.
It works by using an eyepiece.
Mm-hmm. An eyepiece.
So it's oculare in Italian.
Yes, oculare.
I didn't know.
No,
Okay.
no. It's no. Good point. Good point. I hadn't
It's
really
not
sort of
similar to Italian, so eyepiece.
Okay, so this is the main, let's say the main lens, which is close to the sample, and this produces an image which is then magnified by the eyepiece at the other end of the tube. Okay, so this is the situation that we've got, and you focus it by bringing it closer or further away to the sample. Okay.
Okay, so it works by using an eyepiece to magnify the image made by the main lens called the objective.
Ah, okay. Yeah, no. Thanks, Livio. I just don't know what's. I've got no idea what this is. Marina, what are you doing? Cosa fai? Do it again, because these lines.
It's a picture. It's not a video.
No, she's obviously expressing herself. But the thing is, I don't know how she's doing it on this screen.
On your screen.
On my. Oh well, I don't know how it works. Is it? If the screen is shared, are other people able to draw on it? I mean, I know I can. Okay, but I didn't know that other people could. Well, you live and you learn. Okay, I'm going to move on. The only thing is, I've now got this stuff. Can I get rid of it? Evidente gomma. Okay. Yes, I can. There we go. You live and learn. Si impara qualcosa di nuovo ogni giorno. Okay. Right, Anna, do you want to carry on?
Yes. A little later, another Dutchman called Anthony van Leeuwenhoek was the first person to build microscopes powerful enough to see living things in a drop of pond water. His incredible instruments were actually simple microscopes and used a single piece, a spherical lens, which he had perfected how to make. In fact, when he died, no one really knew how he had made the tiny lenses because the instructions he left were very vague.
Un attimo, scusami, sposto qua. Okay. Yeah. So no one really knew how he made the tiny lenses because the instructions he left were very vague. Do you know what vague means? It's a bit like the Italian.
Okay. I understand.
Un po' vago.
Okay.
Yeah. Okay.
His microscopes were by far the most powerful, yet built with magnifications up to 270
times.
And he was able to see larger bacteria.
Bacteria, yes. Okay, I'm just going to see if I can come up with one of his hook. Okay, let's see. There are some famous paintings of him with his microscopes, but his microscopes were really quite incredible. Right, this. Let me just sort of make that a little bit smaller. But this. It doesn't look like a microscope at all. Basically, let's just see if I can increase that a little bit. Yeah, okay. if you go on the internet, there's actually a guy who makes these as replicas. This is the lens, this thing here, this tiny, tiny hole. This needle, this is where he put the sample, okay? And he focused it using these screws. He moved it up and down, okay? So he was able to move the sample up and down. So how did he actually use these? Well, there he is, and there is a photo. There is a drawing of him somewhere using one of these things. There's a famous painting. Where is it? Yeah, okay. Well, this will do. But basically, what he's doing is he's holding this tiny thing up to his eye, and he's drawing. This is amazing, because it's difficult enough to have a proper microscope and move it around and see stuff, but to do this is just unbelievable. I mean, you know, he must have had immense patience. He's an interesting guy, though. He was actually a what's called a draper. He was a textile merchant, and this was his hobby. And this was how he spent his free time, and he worked out how to make the spherical lenses out of glass, good quality glass. But the problem is, he didn't really tell anybody, and so when he died, no one really could repeat his experiments. So what actually happened was Robert Hooke, who he was in correspondence with van Leeuwenhoek. Robert Hooke used the compound microscope because it was easier to make. And the compound microscope basically became the workhorse of microscopy. But van Leeuwenhoek actually had a much more powerful instrument. The compound microscopes were like 9, 10, 20 times, but this was like 10 times more powerful. So anyway, there you go. So this is van Leeuwenhoek, and he drew there this famous engraving of him. He must have had awful eyesight because doing this with a candle, good Lord. Anyway, okay, so that's I get too excited about this stuff because I just love the history. Okay, so Ivo, do you want to sort of take us a little bit further, because maybe there's some lights.
Okay. In the mid 1800s, Carl Zeiss and Otto Schott made great improvements in the quality of the glass used, and also in understanding the limit of the size of things that they could actually see, which is known as the resolving power.
Okay. You probably recognize certainly Zeiss.
Carl Zeiss is a very, very famous.
Is certainly a name that you recognize, but Schott, if you ever work in a sort of a technical environment where glass is used, you will come across Schott glass as well, because it's very particular. It has very particular properties. Okay. What about this? What about the next bit?
Can I read?
Yes. Yeah. Sorry. Yeah. Go.
Okay. Hebby, who worked for Zeiss, found that the smallest things that could theoretically be seen using a powerful optical microscope was about 200
nanometers.
This is called the Hebby limit in his honor.
Okay, so this is I find this fascinating because Zeiss basically worked out how to make really good optical glass, and within a very few years he had it was a factory, but he had people working. These guys basically invented modern optics. Abe was one of his co-workers, and he worked on basically finding how far you could push these instruments. Okay, so this is I think this is quite it's quite curious that we have this. Okay, I think this is the last page. So I know it's 6 o'clock, but if you don't mind, we could, since we started a little bit late, we can finish this now. Marina, are you available? Are you in a car?
I'm in the car.
Okay, no, it's okay. Just forget. It's okay. It's okay.
Today the journey is very difficult.
It's okay. Mi spiace. I'm sorry about that. I'm sorry that it's not so.
Are you driving?
Our song, okay.
I think she's listening. She is in the car now, and I think she's listening to us. Okay, Livio, this you can take this a little bit further if you want.
In the 1930s, Rudenberg and Ruska, working at Siemens in Germany, built the first electron microscope, which uses an electron beam instead of light. This allowed them to see many of the smaller objects in cells, such as the organelles, in great detail. Ruska got the Nobel Prize for his work. The electron microscope can be used in two ways. One is like the light microscope. The electrons pass through the sample being observed. This is called the transmission electron microscope, TEM. The other is used to observe the electrons that reflect from the surface of the sample. This is like using a normal microscope to look at a solid sample on which you shine a light from above.
Okay, so basically what you've got is you've got these two ways. The TEM is the electron equivalent. I'm not going to say electronic equivalent because I don't like that. It's the electron equivalent of the light microscope, because the electrons actually pass through your sample and they cook it as they go. Okay, the SEM, which is the scanning electron microscope, is used widely for looking at surfaces. So when you see those really fantastic pictures of insects, like ant heads and stuff that are really, really sort of detailed, they're typically done with a SEM. Okay, so there's two different ways of using this, and the discovery, the work of Rudenberg, that in itself is a very interesting piece of history. Okay, guys. So I hope this was okay, and I hope this was interesting for you this week. It's a shame that we only have, there's only a few of you this time. I don't know, but I think it is the season for staff meetings and meeting parents of students, which is maybe not so interesting. And I don't think you can get out of it. So anyway, okay. So if you have any comments, any questions, just please, please do ask, do get in touch with me. Okay. So if everyone's okay, I will call this an evening, and I will see you next week, hopefully.
Okay.
Yes.
A very interesting lesson for me.
Thank you, Livio. Thank you.
Gardo.
Also for me.
Thank you, Anna. Ivo, tell me.
About the optics, It was the lesson we skipped the last time.
No. What I've done, last week I didn't do a lesson, so I've just
yes, I remember. We participated at the end of the course.
Exactly.
Okay.
So this was what I was planning to do last week.
Okay.
So it's just been moved. That's all. You haven't missed anything.
Okay. Thank you.
Okay. Right. So thank you very much, and we'll see you again next week. Okay. Hopefully, please.
Okay.
Thank you.
Okay. Right. Thank you. Bye.
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 Have a good evening, everybody. Thank you.
Bye.
Thank you. You too.
Bye.
Okay. So I need to lascio la riunione.